Hello, this is Julie Lerman.
And this is Steve Smith.
Welcome back to Domain-Driven Design Fundamentals. In this module, you'll learn more about aggregates and the associations between entities.
We've talked about the domain model and the need to have effective communication in order to ensure the model is a useful representation of the customer's problem space. However, most problems that warrant using domain-driven design can be quite complex, so now we're going to specifically look at some patterns and techniques that can be used to manage this complexity.
We'll cover several new terms along the way, including aggregates and aggregate roots. You'll learn about invariants and the aggregate root's responsibility for them. Aggregates often contain related data, so we will explore how to model relationships, often referred to as associations, in DDD.
Then we'll look at our application and see how thinking about the aggregate roots pattern helps us revise and simplify our model.
And finally, we'll walk through how we've implemented this pattern in our code.
Let's start by considering data complexity. If you've ever worked on a relatively large or mature application, you've probably seen some fairly complex data models. One way to reduce the complexity that we already talked about is using aggregates and aggregate roots, which you've seen in the DDD mind map. Another is by limiting how many bidirectional relationships you have in that data model.
If your design doesn't have any clear notion of aggregates, the dependencies between your entities may grow out of control, resulting in a model like this one. And if your object model reflects a data model like this one, trying to populate all of the dependent objects of one object might result in trying to load the entire database into memory. And the same problem exists when it comes time to save changes. With a model like this, there's just no limit to which areas of the data model might be affected.
Even though in the real world, at the highest levels of your system, all of these things really do interrelate, we need to be able to separate them to keep the complexity of the system in check.
I've gone into a lot of clients where their entity data model looks like this, and they're using this one big, huge single model throughout their entire system. So one of the things that I work on with them is breaking this down and using the whole concept of bounded contexts to start looking at what makes sense for smaller models.
Yeah, a system that's designed like this is what we tend to call a big ball of mud, because everything is just kind of slapped together and it collapses under its own weight once it gets to a certain level of complexity.
Great. So let's see how we can use aggregates to help solve the problem. Aggregates consist of one or more entities and value objects that change together. We need to treat them as a unit for data changes, and we need to consider the entire aggregate's consistency before we apply changes. In the examples shown here, the address is part of the customer, and the component is quite literally a part of the product. We can treat a set of changes to a customer and their address as a single transaction. Every aggregate must have an aggregate root, which is the parent object of all members of the aggregate. And it's possible to have an aggregate that consists of just one object, in which case that object would still be the aggregate root.
In some cases, the aggregate may have rules that enforce data consistency that apply across multiple objects. For instance, maybe our product consists of a collection of components, but in order to be in a valid state, it needs to have a specific set of such components. As an example, if the product is a Lego minifig, the collection of parts won't be a valid product unless it includes a head, an upper torso, a lower torso, 2 arms, 2 hands, and 2 legs. If we allowed the collection of components to be modified independently of the product it was associated with, we could easily end up with consistency problems. If we want to modify the composition of a product in this example, we should do so as a transaction so that we start and end with a valid product.
Data changes to the aggregate should follow ACID. That is, they should be atomic, consistent, isolated, and durable. It's also the responsibility of the aggregate root to maintain its invariants, such as the number and type of components it requires in the example. An invariant is a condition that should always be true for the system to be in a consistent state. When considering whether a particular object should be treated as an aggregate root, you should think about whether deleting it should cascade. In other words, if you need to also delete the other objects in its aggregate hierarchy. If so, it's likely the object in question should be considered an aggregate root.
Another way to think about whether it makes sense to have an object as an aggregate root is to ask, does it make sense to have just this object detached from its parent? In the examples shown here,
If you're deleting the minifig, then you have to delete all of its parts. Conversely, if you have to delete a head, maybe it got broken, you don't need to delete the rest of the parts. Therefore, it doesn't make sense for the head to be the root of this aggregate.
In the Domain-Driven Design book, Eric Evans states this pretty simply. He says, an aggregate is a cluster of associated objects that we treat as a unit for the purpose of data changes.
When considering aggregates, which as Evans said is a cluster of associated objects, it's also important to think about relationships between those associated objects, especially those which exist within the aggregate. Before diving into how related entities participate in an aggregate, it's important to learn some important concepts that DDD brings to us when considering relationships among entities.
Many developers, myself included, tend to define relationships between classes in both directions. For example, an order has a line item and a line item has an order. A pet owner has pets and a pet has an owner. Many of us tend to think in bidirectional relationships by default. Because domain-driven design aims for simplicity in the model, we start recognizing more quickly that the bidirectional relationships can often make things overly complex. For instance, I've often found this to be true when it comes to adding in my persistence layer, and I happen to mostly use an ORM, Entity Framework, which brings along its own behavior and assumptions about how relationships are managed. Sometimes the fact that my model includes navigation properties that may not be totally necessary can be the cause of some grief that's led me to take some time to consider if I really need that navigation or not.
Domain-driven design guides you to default to one-way or unidirectional relationships. That's not to say that you shouldn't ever have bidirectional relationships, but that because of the extra complexity involved, you should spend some time considering if that complexity is justified.
A relationship, also known as an association, should be part of a type's definition, and we do that using properties that allow us to traverse from one end of the relationship to the other. In this example, we have a client type with a patient's property, and in the patient type, we have a client property. Not just an ID value, but a property that leads to a complete object or set of objects. If you introduce a bidirectional relationship, as shown in this code, using properties that let you traverse in both directions, you should only do so when neither object can be defined without the other. If that's not the case, then you need to be specific about the direction of the relationship, also called the traversal direction, to keep your model design simple.
Eric Evans puts it this way. A bidirectional association means that both objects can be understood only together. When application requirements do not call for traversal in both directions, adding a traversal direction reduces interdependence and simplifies the design.
So with a DDDI, we can look at our model and ask, can we define a client without identifying their pets? Can we define a pet without identifying the client who's responsible for them?
This may sound like a simple set of questions, but it could lead to a whole lot of debate. For example, why would a person be scheduling an appointment if they didn't have a pet? So in the context of scheduling appointments, a client doesn't make a whole lot of sense without one or more pets or patients.
Or from another perspective, a cat can't pay a bill or call to make an appointment. So how can we define a pet without a client? These are both pretty reasonable arguments, but neither one gets us anywhere.
So let's start again with defaulting to a one-way relationship. A client would need a patient to schedule an appointment. A client would not need a patient to pay a bill.
Okay. And if we started from the patient end, a patient doesn't schedule an appointment, so that becomes a moot point. Nor does a patient pay the bill. And, because my dog doesn't have a credit card. He can't use the phone very well either. So when would you start with a patient and need to know something about the client responsible for that patient? That's an interesting question. So, in the context of scheduling an appointment, one could argue that we should define the traversal from client to patient, and that we gain nothing by having a way to traverse from a patient back to a client. You may balk at that notion, but remember that all we care about right now is scheduling an appointment, not all the other possible scenarios where it might make sense to traverse from patient to client.
Sure, it's another example of Yagni. You're not going to need it. In fact, we originally had owner as a property on patient in this context, but we
Yeah.
realized it wasn't necessary, so we removed it. However, we kept the ID because we had some scenarios where it was useful.
So in the end, we chose to define relationships that traverse from appointment to doctor, patient, and client, and to define one that traverses from client to patients or their pets, but not the other way.
You may have experienced another type of bidirectional relationship problem if you've seen related data get serialized in your applications. When objects are serialized, the serializer typically traverses all of the object's properties recursively. If there is a bidirectional relationship, it can create a loop that will cause serialization to fail. You can think of saving aggregates in much the same way, and in fact, depending on how your persistence layer is implemented, serialization may actually be required as part of how your app persists its aggregates. In our aggregates, the single direction that we would use would go from the root to its dependents, and never the other way around.
Aggregates serve as boundaries between logical groupings within our application. We enforce these boundaries by prohibiting direct references to objects within an aggregate that aren't the root of the aggregate. Consider the customer with the address. It's perfectly okay for customer to reference address. Address might be an entity or it might be a value object. It doesn't really matter in this scenario. What's important, though, is that the only way to get to the address in this aggregate is through the customer. We won't be referencing an address by some identity outside of this aggregate, but that's not the case for customer. Since the customer is the aggregate root, it can be referenced from other aggregates.
In this common example, an order might reference a customer. Depending on our context, it might make sense for a customer to reference an order. In this case, let's assume it only makes sense for the order to be central to the application's design. What's not okay is for the order to reference a customer's address directly. This violates the integrity of the customer aggregate.
Remember that aggregates and aggregate roots only apply to objects, not data. And when we're talking about references, we're talking about object references, properties that use an object directly. This is especially important with ORMs. For example, if you were to save an address that had a customer object attached to the customer property, there are scenarios in which Entity Framework would involve the customer in the database insert or update, possibly even a delete. And this behavior leads to a lot of confusion. I frequently advise developers to just remove the navigation property and use the foreign key ID instead. It's a little more work, but removing some of the ORM magic results in more control over the behavior. And this aligns perfectly with the fact that one common way to enforce aggregates is to replace direct navigation properties in the model's non-root types with key references, and this reduces the number of dependency relationships within the model.